Okay, we've got one class that's already into chapter 5, another class that's just getting toward the end of chapter 3, and we had some questions because not only everybody here today was in the chapter 3 group, and they're approaching rational functions. So even though we've talked a lot about rational functions, and you want to look at videos, other videos I've done on rational functions if you need them, and they're on the assignments page. We did something that's really just an introduction again to rational functions with about 3 examples. So first of all, rational function is a function r of x in the form of a polynomial divided by a polynomial. Okay? A couple of characteristics. If the numerator is 0 and the denominator isn't, then r of x is 0. Now in the case where the numerator is 0 and the denominator is, well, I'm not going to talk about that in introduction here. But that's a case you've got to deal with later. But in this case, well, if the numerator is 0 and the denominator isn't, you know you got 0 up here and you don't have 0 down here, you're going to get 0. If the denominator is 0 and the numerator isn't, r of x has a vertical asymptote, because then your numerator isn't 0, your denominator is. As you approach that 0 of the denominator of this rational function gets very tiny. The numerator doesn't. So very tiny goes into something that's not very tiny as many times as you want, meaning that your quotient is either going to approach infinity or negative infinity. And that gives you a vertical asymptote. And often it'll approach infinity on one side, negative infinity on the other, depending on the degree of the 0 here. Okay, r of x can change sign. This is very important. The only place r of x can change sign is at a vertical asymptote or a 0, meaning it can only go through the x-axis. It can either switch sides of the x-axis, either at a 0 or a vertical asymptote. And it doesn't have to change sign, as you know from polynomials. That depends on the degree of the 0. Okay. If the degree of the denominator is greater than the degree of the numerator, then the end behavior is asymptotes with the x-axis. The graph is, that's not a very literate sentence, but the graph is asymptotic to the x-axis. Okay, meaning that the graph is going to approach the x-axis on both ends. If the degree of the numerator is 1 greater than the degree of the denominator, the end behavior is what we call a slant asymptote, and we'll demonstrate that in the next example. But we're going to start out with this example. R of x is x minus 1 divided by x plus 3. For this function, the numerator is 0 when x is 1, denominator is 0 when x equals negative 3. So if you start constructing the graph, you first write the 0 at x equals 1, and that would be here. And maybe I could have drawn a little arrow to indicate that that's your 0 at x equals 1. The vertical intercept, you always want to calculate the y-intercept by letting x equal 0. Well, clearly if x is 0, you're going to get negative 1 over 3, negative 1/3. So your y-intercept is at 0, negative 1/3. The vertical asymptote is at x equals negative 3. Okay, so here's your vertical asymptote. And then we sketch the graph using that information. And we know that the graph is negative here. We know that it is 0 here, has a vertical asymptote here, and there are no zeros or vertical asymptotes between here and here. So the graph has to stay negative between here and here, meaning that the vertical asymptote is going to be on the negative side, on this side of the vertical asymptote. The behavior of the function is going to be negative. It's going to go down toward negative infinity. We also know that since the degree of the numerator equals the degree of the denominator, you have horizontal asymptotes with the x-axis. So once we get up to this 0 here, we've got to come back toward the x-axis and approach 0 as x approaches infinity. So we're going to come through here, it's going to have some kind of a positive slope, so it's going to keep going up for a little while, but it's got to turn around and approach the x-axis as an asymptote. So it's going to pretty much, after reaching its maximum, come down here and pretty much flatten out. On this side, well, x is less than 3, so x minus 1 and x plus 3 are both negative, so that r of x is positive. So you're going to you're going to stay above the x-axis, but you've got a horizontal asymptote here and a vertical asymptote here, which gives you pretty boring behavior. It's just going to do this, pretty much like a reciprocal function, the 1 over x function. So there it is. Okay, that's that example. Now, second example, and we're going to end up with a slant asymptote, is this function. R of x is x squared minus 4x minus 5 divided by x minus 2. The numerator is 0 if x squared minus 4x minus 5 is 0, because, of course, that's the numerator. And we've always got to check. If we got any kind of a polynomial, we've always got to check for its zeros. Well, we set it equal to 0 and see if we can solve the equation. In this case, it's very easy because this expression factors. It's a quadratic expression. If it didn't factor, well, we could use the quadratic formula to find where it's 0. And that would tell us where the zeros of the function, the rational function, are. And at neither of these zeros is the denominator 0, so we know that these are both going to be zeros of the function. Okay, I didn't write that down, I didn't mention it, but clearly the denominator isn't 0 here, it isn't 0 here. So we fulfilled the condition that the numerator is 0, the denominator isn't. Denominator is 0 if x equals 2, the numerator isn't, because the numerator is only 0 at negative 1 and 5. So we have a vertical asymptote at x equals negative 2. And also the degree of the numerator is 1 greater than the degree of the denominator. So in that unique situation, we have a slant asymptote. We'll determine the slant asymptote in a minute. Okay, so we put the 0 down here, the zeros, at 5 and negative 1. The graph has to go through 0, through those zeros. And it has to go through the vertical intercept, which is easy to find, that it's going to be 5 over 2. It has a vertical asymptote at x equals 2. And I didn't really label that, and I should have. Now we still have this slant asymptote. How do we get the slant asymptote? Well, we divide the denominator into the numerator and see what we get. Here we have it. We're going to divide the numerator by the denominator. We're going to do a long division. Not sure that you've seen that yet in your course, but you will, so I'm not going to go over the details of long division except to do an example. And if it turns out in your course that you have trouble with long division, we can come back to it here. You just got to ask. Okay, so we do the long division. Now, x goes into x squared x times, because, of course, x squared divided by x is x. If we then multiply x by x minus 2, we get x squared minus 2x. Now, you see this little red minus sign and little red plus sign. What's that doing there? Well, we got to subtract this expression from what we have from our original polynomial to see what we've got left after we have the x. Okay? So x times x minus 2 is going to give us this. We've got to see what we've got left and see how much x minus 2 divides into it. I put the little negative and positive sign here to remind myself that I'm subtracting this, which means that I've got to actually subtract x squared from x squared, and I've got to subtract 2x from negative 4x, negative 2x from negative 4x, which means I've got to add 2x. So just a matter of keeping track of my signs. And you see how you're instructor in the regular course goes about this? Well, I do this and I get negative 2x. I add this to this, get negative 2x. Of course I do x squared and negative x squared, I get 0. Then I bring down the negative 5, just like you do in the long division algorithm you learned years ago. And I divide the x into the negative 2x, I get negative 2. Multiply negative 2 by x minus 2, I get negative 2x plus 4. I put little red signs here to remind myself what I'm doing. So I'm going to do negative 2x and then a plus 2x to subtract the negative 2x, giving me 0. And negative 5 and negative 4 gives me negative 9. And that's my remainder. X minus 2 won't divide x minus 9. So I write then my remainder over x minus 2. And there is the function. If I multiply this by this, I should get this. If I've done the long division correctly, it turns out that I did. It's easy to lose a step. You know, I can do it as well as you can. So I've got to check. And if I've got to check, you've got to check. Okay? You got to check. And the check convinces you of why the slant asymptote is where it is. Okay? Why is that? Well, this function then, if I've done this right, is equal to this times this. I'm sorry. This function, this r of x function, is this divided by this, which is equal to this. So this is just another way of writing that function. Well, to check the division, we multiply the divisor by the quotient and see if we get the original term, which is called the dividend. Okay, we check, we do this multiplication. Well, to do it, I multiplied the x by all these terms first. And then I multiplied negative 2 by all these terms. And I got this and this. Now I made a couple of sign mistakes. You see where I had to smudge stuff out. But, okay, there we have it. And then I combine terms. I'm going to get an x squared. We've just got an x squared. I've got a negative 2x. Negative 2x gives me minus 4x. I've got my 4. And for some reason I wrote that over here because I got hung up on this term and this term and this term. And that's where my attention was, so I just wrote it out of order. In any case, this term and this term both have the same denominator, so I can write this as negative 9x plus 18. So right there's my product. Well, negative 9x plus 18 simplifies. If I factor out a negative 9 from the numerator, I get negative 9 times quantity x minus 2. You multiply this out and see that you get this. And you might wonder why I did a negative 9. It's because then the x minus 2 is going to match the x minus 2 here. And I'm just going to end up with negative 9. So now I've got x squared minus 4x, and this is a negative 9, and this is plus 4. Which gives me x squared minus 4x minus 5, which is the original numerator. Okay. Now since this is the numerator divided by the denominator, this is another way of writing the function. And we can see that when x gets really large, whether it's positive or negative, the denominator here is going to get huge. And when we divide a huge number into 9, we're going to get something that's really tiny. And in fact, as x approaches infinity or negative infinity, this is going to approach 0. And we're just going to end up with x minus 2. Well, in blue here, now I've got my graph of y equals x minus 2. The scale's a little bit, this doesn't look like a graph with a slope of 1 because my 5/2 here is smaller than 5/2 would be here. So it tends to flatten out the graph a little bit. But I've sketched the graph according to this. According to the fact, first of all, that when x is a large negative number, we've got to be close to x minus 2, meaning the graph has to be close to this slanting line. And when x is a large positive number, we've got to get close to the slanting line once more. We've got to go through 0 here. We've got to go through this point. We've got to be asymptotic here. So the graph has to do something like this. And over here, we've graph again has to be asymptotic. It's got to be positive over here. It's got to go through the 0 here because the degree of the x minus 5 that gives you this 0 is 1. And that means it's got to be negative here. So it's going to do this. Okay, so that's an example of a slant asymptote. Now there's one more example. It's pretty easy to dispose of. And that's this function, which is clearly 0 when x is negative 3, or negative 1, or 5. Those are the degrees, those are the zeros of your numerator. None of these makes your denominator 0, so they're all zeros of the function. The denominator is 0 at x equals 3, so we have zeros here, here, and here, and we have a vertical asymptote here at x equals 3. And I guess I haven't labeled those really clearly, but here's 3. The y-intercept is 0, 5. If x is 0, then you're going to get 3 times negative 5 times 1, which is negative 15. You're going to divide that by the negative 3 from the denominator, giving you 5. Okay. The degree of the numerator is 2 greater than the degree of the denominator. And I didn't have time to go over this in detail, but we can talk about it later if you don't understand it in your course. That means the end behavior is essentially that of a quadratic function, of a degree 2 function, which gets big on this side and gets big on that side and then has a vertex down here somewhere. That you don't end up with that vertex because of all the other stuff that's going on, but that's essentially why you have a rapid approach to infinity on this end, just like you would with a parabola, and a rapid approach to infinity on this end. Now, another way of saying it, if x is large, r of x is a huge positive number. Okay? And you can check that out in various ways. In other words, r of x increases more and more rapidly as x goes to infinity or negative infinity. So, it's got to go up like this. It's got to go up like this. So we start the graph up here, come down through the 3, up through the 1, through the 0, 5, and then asymptotic to this vertical line. And then here, we got to be up here on this end. We got to go through 5 because the degree of this 0 is 1. And means we've got to go down toward negative infinity here. So there's the graph. Now there are a lot of details that you need to work through, and you will work through in your course. And of course we can work through them here if you have need of that.